Hello everyone and welcome to McCaulay's 360. So in this video, I want to solve a problem with you to illustrate the concept of the McCaulay's principle or the singularity function. Okay, McCaulay's method. All right. So now this is where we are going to begin from. We have a beam which is of length 6 meters. Okay, and it is simply supported at its end, and then it carries 2 point loads of what 48 kilonewtons and 40 kilonewton at a distance of what 1 meter and 3 meter or 3 meters respectively from the left support. Okay, so we have to find the deflection under each load, and then we should find the maximum deflection as well as the point at which the maximum deflection occurs. All right, so this is a typical question under singularity method. All right, so everything that was mentioned here is the diagram here. Okay, but sometimes in exams, in a typical exam question, you will not be given anything here, but basically whatever we said in the problem is what we've drawn here. All right, okay, so basically if you have something like this, the first thing to do is to look at your statics. All right, or how can we first of all find the support reactions? Okay, that is the first thing to do, to find the support reactions. So let's go ahead and find the support reactions using our basic knowledge in mechanics or our statics. So first of all, we know that if a rigid body is in equilibrium, summation of forces should be 0, right? So let's begin. RA is going up, so plus minus 48, which is coming down, minus 40, which is coming down, plus RB. Okay, so if we add, if we arrange the terms together, we have RA plus RB. Let's add 48 to 40. That is going to be 88. So let's call this equation 1. Okay, now after summing forces, we need to sum moment. So maybe we can decide to sum moment about point B. So we are going to sum moment about point B. Then we will just say that clockwise is what? Positive, should be 0. Okay, so if we say clockwise is positive, should be 0, then it means that we are going to sum moment about this point. Okay, starting from RA. So RA is going to create a moment in this direction, which is clockwise. Okay, so it's going to be plus. So RA multiplied by 6, that is the distance from RA to B. All right, and then I will multiply 48, which is this force, by the distance. All right, so the distance from 48 to B, what is it? So the whole of this length is 6, but then from here to here is what? 1. So meaning that the distance from 48 to B will be what? 5. Okay, so that one, but then this one, you see that the 48 is causing a moment which will go in the counterclockwise. So it's going to be 48 multiplied by 5. Okay, and then of course, if this distance from here to here is 3, then we expect that from 40 here to this B must be what? 3, right? Because it is almost halfway. All right, so it's going to be and that one also counterclockwise, so it's going to be minus 40, then you multiply by the 3. Okay, if you do that, you are going to is there any other force? No, so you just equate it to 0. All right, now let's solve for RA. So solving for RA, let's group everything together. So it's going to be 48 multiplied by 5 plus 40 multiplied by 3. Then we divide everything by 6 so that we can get RA. And what is that? Let's do it together. So we have 48 multiplied by 5, and then plus 40 multiplied by 3. Then we divide by 6. And if you do that, we are having 60. So RA is 60 kilonewton, meaning that the RA which is here is what? Is 60 kilonewton. So if this is RMA, then let's go back to equation 1 and put RA equals 60, so that we have RB is going to be what? 88 minus RA, but then RA is what? Is 60. So we have 88 minus 60, which gives us what? So we've got 88 minus 60, so 28 kilonewton. So in other words, RB is what? 28 kilonewtons. Okay. So in fact, we just started. Okay, we've not started the strength of materials. All of this is your basic mechanics. Now we're about to start our strength of materials by looking at the deflections. Okay. So according to McCaulay's method, whenever you have something like this and then you want to find the deflection, what you have to do is that you take a section along the beam, and the section will be such that you are going to take the section to cover almost all the load, or let's say most of the loads. But then it doesn't make sense to cut it such that at least if you cover one of the reactions, it's okay, because you cannot say that, okay, you want to cover all the loads, so you come and stand there and cut. There is nothing here, but I can stand somewhere here and make a section, right? If you make a section like this, it means that at least it has covered this reaction force and then also these two loads, so that will be okay. Now, as soon as you take the section, what happens is that you have created a distance from the origin. So let's call this point A here, let's call it x equals 0. You have created a distance from all this way up to where you have taken the section. Let's call that distance maybe say x. Okay, let's call that distance x. Please take notice that the section that we have taken, it doesn't mean it means that this distance is not 6. 6 is actually from the first the starting point to the ending point. That is 6. But if you take a section, it is not 6 again. Okay, all right. So we've got x here, but then let's ask ourselves, from here up to here is 1. Okay, meanwhile you know that this is 1 and then the whole of this is x. So if this point is if this distance is x and this is 1, then you want to ask yourself that what is the whole distance all the way up to here? Okay, that is the question we need to ask ourselves, and that is very simple. It's going to be what? X minus 1. Similarly, if the whole of this distance is from here to here, from here to here is 3, but we know that the whole of this distance after the section is x, then to get this small portion, what do you have to do? Simple. It's going to be x minus 3. Okay, so that is how we do something like this, and we call it the McCaulay's method. All right. So once you have gotten this, it's going to be simple and straightforward. Now, maybe I can clean the reaction because now we've gotten it already. All right. So I will clean the reaction forces, and then we will begin coming up with the deflection. All right. So at this juncture, this is what we are going to do. Once we've been able to introduce a section, it means that there is going to be a shear force in this direction, and then there will be a bending moment due to the section that we have taken. All right. Okay. So now this is what we are going to do. First of all, we are going to sum moment. Okay, let's sum moment about the section. So let's call it m of x clockwise is positive to be 0 for equilibrium. But then don't forget that there is already a moment mx due to the section that we took. So let's call that so it's going to be counterclockwise. So it's going to be minus mx. Okay, all right. And then let's start from the reaction here, 60. So 60, and the distance from the reaction to where the section is, that is the x. So then it's going to be, and then the the moment is going to come in the clockwise sense. So it's going to be plus 60 x. Okay. Then we will come to the 48. You see that the distance that we made, you see that this one from here to here is 1, but all the way up to here is what? X minus 1. So we will use that one. So then it's going to be but then the moment is counterclockwise, so it's going to be minus. So minus 48 into what? X minus 1. Then you come to the 40 kilonewton. You see that the distance that you have gotten from here to here is x minus 3. But then you also see that the load is coming downwards, and then the moment is going to come this way. Okay. At this point, I expect you to understand movement. Okay. So it's going to be counterclockwise. So then it's going to be minus 40 into bracket x minus 3. And if you do this, you can equate it to 0 because we are done with the forces. Okay, so at this juncture, we can say that our mx that we are interested in will be what? Will be 60x. So we just have to take the mx to the other end. 48x minus 1 minus 40x minus 3. So this is our moment. But what do we know? We know that ei d squared dx squared, d squared y over dx squared is what? The moment that we want. So we just have to equate this to the moment. That's all. So 48x minus 1 minus 40x minus 3. Okay. So once we get to this point, the strength of materials has ended because now we are going to use calculus. So we are basically going to use the method of calculus. Okay. So then let's continue. So this is what we are going to do. We will integrate the function that we have here. Okay. So that we will get ei dy dx. Okay. So let's integrate it together. 60 is already there, so we will not touch it. Let's integrate x. It's going to be x squared divided by 2. Okay. And let me teach you something important here. Please, this expression that you see here, x minus 1, is a total expression. So when you integrate it in the McCaulay's principle, you will integrate the whole of this. So it's going to be like x minus 1 squared divided by 2. You will not try to open it and integrate it separate, please. That is how the Macaulay works, please. So this one too, you do the same thing. You are going to assume x minus 3 as a whole and then you integrate. Okay. So if you do that, and then you have to bring a constant C1 because after integration you need to bring a constant. Okay. So at this juncture, we've been able to set up the slope. And once we've been able to get the slope equation, then it means we can go ahead and get the deflection. So if I integrate slope, I get deflection. Okay. Again, this time around, I'm going to take my time and do it. So we have 60 divided by 2 one side. Then what is the integral of x squared? That is going to be x cubed divided by 3 minus 48 on 2 one side. Then I'll do x minus 1 cubed divided by 3 minus 40 on 2 one side. Then I'll do x minus 3 cubed over 3 plus c1x and then plus what? C2. All right. Now, once you've gotten to this portion, we would have to go back and then establish some boundary conditions. Okay. So let's establish some boundary conditions. So if you look at the beam carefully, this is a simply supported beam. And for a simply supported beam, what happens is that the deflection will be of some nature. It's going to be something like this. Okay. Now, actually, because of the orientation of the loads, it's not going to be the normal simply supported beam which will act something like this. No. Okay. But then what we are trying to say is that at this portion, let's call this portion x equals 0. And let's call this portion x equals L. You see that at those portions, the deflection will be 0. So we say that at s equals 0, y is 0. And then, so this is what we are trying to say. At x equals 0, our y will be 0. And then at x equals L, which is 6 meters the length, our deflection y is also 0. So let's put everything inside and see what will happen. First of all, x is 0, y is 0. So everything is 0 minus 0 plus 0 plus C2. So C2 is 0. Please, let me warn you about this. You see that we could have placed 0 here so that you have 0 minus 3, which is going to be minus 3. And this one too will be minus 1. But please, in the Macaulay, whenever you put the distance inside and it is negative, we assume that it is 0. Okay, whenever you put the distance inside and then it's negative, we assume it's 0 because it doesn't make sense to measure distance and get 0. So then you will assume that it is 0. Okay, again, let's put another boundary equation into it. At x equals 6, y is 0. So you see that y will be 0 here. Okay, let me take my time and do it. EI multiplied by 0 should be equal to what? This time around, this is 60 divided by 6. Okay, and then x cubed, which is 6 cubed, minus 48 divided by 6, x minus 1, which is what? So 6 minus 1, which is, okay, let me just take my time and do it. And then so at this point we have minus 40 over 6, and then we have what? 6 minus 3 cubed plus 6, which is the x c1, but the c2 is 0, so we don't need to bother about it. So please, let's solve for c1. So we have 0 is equal to 60 divided by 6 is going to be 10, but let me do it to get together with you so that you'll be happy. 60 divided by 6 is 10, so we've got 10. No, let's multiply everything. So it's going to be 10 multiplied by 6 raised to the power 3. Then minus, so minus 48 divided by 6. Then 6 minus 1 is 5 raised to the power 3. Then minus 40 divided by 6. 6 minus 3 is 3, right? Cubed. Okay, so what is it going to give us? 980. So we can say that 980 plus 6 c1. Therefore c1 is what? Minus 980. Then we divide. So then we will divide it by 6. And what is 980 divided by 6? Divided by 6. So minus 163.33. Okay, so that is the C1. So you know what? Let's take our time and write the whole expression again. But this time around, we are going to include the C1 we have found. And then the C2, we know that it is 0. Okay, so let's do it. So 60 divided by 6, we said it is 10. So EIY will be equal to what? 10x cubed minus, and then we do the same thing for this 48 divided by 6. So 48 divided by 6, 8. So minus 8 x minus 1 cubed, and then minus 40 divided by 6. So 40 divided by 6, okay, let me just write it as 20 on 3. X minus 3 cube, and then plus C1. Okay, so 163.33 x. But then the C2 is 0. So that is it. So in fact, this is actually our equation for the deflection. All right. So once we have gotten our equation for deflection, we have to put the deflections inside. So for instance, if I ask you that what is the deflection, so if I ask you that what is the deflection at under the load 48 kilonewton, I'm just trying to tell you that what is the deflection at C. In other words, what will be the deflection at x equals 1? That's all. So to put it inside is going to be the first part of the problem, YC, that is to say the deflection at C. Okay, let me just write it. Deflection at C. So let's do it together. That is to say at x equals 1 meter. So we are going to put our we are going to put everything inside. Okay, so it's going to be EIYC 10 1 cube. You see that if you put 1 inside this one, you get 0. 1 minus 1 is 0. And then 1 minus 3. I told you that whenever you put it inside and then you get negative, you have to ignore it. Okay, so we are not going to use this because of the fact that it's going to be negative. Okay, and then at this point you are going to use this one. I'm sorry, you are just going to use 163.33 multiplied by 1. All right, so that is it for you. So we've gotten okay, let's first of all let's find okay, let me write it here. So we know that YC will be what? 10. So 10 minus 163.33. That is going to be minus 153.33. Then we divide this whole thing by EI. Okay. But the EI that we've gotten, you see, whatever we are doing here is actually in kilonewton meter, right? Don't forget that the load was in kilonewton, and then the distance is also in meters. So to convert kilonewton meter, what we are going to do is that we will just multiply this. Okay, let me take my time and explain what I'm talking about. So I'm saying that whatever we have here is not in millimeters. Okay, so to be able to convert this into millimeters, we are just going to use a convention, and then that convention is that we will multiply the numerator by 10 to the power 12. Okay, because what we have here is actually in kilonewton meter cube. Sorry, it's actually in kilonewton. This answer that we have here is in kilonewton meter cube. All right, so we will have to multiply this. The kilo is 10 to the power 3, and then the meter cube is actually millimeters. So in millimeters, it's going to be 10 to the power 9, okay, which is like 12. All right, so basically we are just going to multiply here by 10 to the power 12, then we divide it by EI. So we are going to divide it by EI, and then E is what? So 2 times 10 to the power 5, and then I is 85 times 10 to the power 4. So 2 times 10 to the power 5, and then 85 times 10 to the power 4. Now, if you are confused with the convention, one thing that you have to notice that the answer that we have gotten is actually in kilonewton meter cube. Because don't forget that the load here is Newton, and then this one is what is also in meter cube. All right, but then if you want to stay in meters, then you will rather convert this one. Okay, but then if you want to just use the millimeters, then you multiply by 10 to the power 12. That's all. So what will be YC? YC is the deflection under C. And what is that? So the deflection under C will be nothing but minus 153.33 divided by 2 times 10 to the power 5. Then we multiply by 85 times 10 to the power 4. And then, in fact, it's 10 to the power 12. Oh, sorry. So what is the answer that we are going to get? So we are going to get, it's actually 85 times 10 to the power 6, sorry. All right, so it's 10 to the power 6 rather. Okay, so in fact the actual answer is 9.019. So minus 9.00019, sorry, millimeters. So if you convert it, that one, the answer will be in millimeters. But if you don't convert it, then your answer will be in meters. Then you would have to convert it back. All right, so we've solved the first part of the problem. Now we need to find the deflection at D, that is at x equals 3 meters. Let's solve for the deflection at this point. So for this point, we are just going to say at x equals what? At x equals 3. That's all. All right. So at x equals 3, let's do it together. So we are going to use the same equation. This one. But we are going to use at x equals 3. You see that if you put 3 here, okay, let's do it. Or maybe let me copy the equation. All right. Okay. So I've copied the equation. Let's put s equals 3 inside. So it's going to be EI YD should be what? 10 3 cube minus what? 8 3 minus 1 cube minus of course if you put 3 here it will be 0, so you don't need to bother, and then multiply by 3. So then YD, so let's calculate what we have here. So 10 3 cubed, right? And then minus 8 3 minus 1 cubed, right? And then minus 163.33, right? Multiply by 3. So we have minus 283.99. Okay. So this minus 283.99 that we've gotten, again, it's in kilonewton meter cube. So kilonewton meter cube. Therefore, we need to convert. And then the conversion is that you multiply by 10 to the power 12. Then you divide by EI again. Which is 2 times 10 to the power 5. Multiply by 85 times 10 to the power 6. Therefore, our YD is going to be what? So the deflection at D, so it's going to be minus 283.99 multiplied by 10 to the power 12 divided by 2 times 10 to the power 5 multiplied by what? 85 times 10 to the power 6. And the deflection we are getting minus 16.705 millimeters. So we've been able to solve for YD. Then the last part of the question is saying that we should find the maximum deflection, and then also at the point at which the maximum deflection occurs. So let's calculate that one, the maximum deflection and the point at which it occurs. Let's do that one. So if you want to calculate the maximum deflection at the point and then at the point which it occurs, we know that for a simply supported beam, the maximum deflection, in other words, at the point of the maximum deflection, the y dx will be 0. But you cannot go forward and say that it will the maximum deflection is going to occur at the center. Now think about it carefully. We are applying loads to this beam, and you see that there is 48 here. You see that there is 40 here. There is nothing here. So if there will be deflection that is going to bend, the bending will actually occur something like this between this and this. That is where the bending will actually be intensive. So if there will be a certain maximum deflection, then it must occur somewhere between somewhere between C and D. Okay, but do you remember that we took a section beyond this one? Then we said that let's go from here up to here, what, x minus 1. Okay, and then we said that this one was what, x minus 3. In other words, we were saying the whole of this is what, x. But then this is what we are going to do, because we are assuming that the maximum deflection is going to occur somewhere between C and D. Then we are going to use only the force which is between C and D for our analysis. You will clearly see that okay, so let me write it. So the maximum deflection is going to be, so the maximum deflection is going to be 30 x squared. Okay, let me go back to the slope. We said that at the maximum deflection, the slope is 0. So 30 is x squared. That is to say 60 divided by 12. Let me copy this one. Okay. All right, so let's try to break it down. It will be EI dy dx is what, 30x squared minus 48. 48 divided by 2 is going to be 24. X minus 1 squared minus 20 x minus 3 squared plus C1. We know C1 already. It was minus 163.33. And then we are saying that to find the maximum deflection, or the point at which it occurs, at the maximum deflection, dy dx is 0. So we are going to set dy dx to 0, but not everything here, but rather we are going to set the portion of the beam where the maximum deflection is likely to occur. And we all agreed that it will occur between somewhere C and then D. That means that since it is occurring between C and then D, then we are not going to use it's going to be 30x squared minus 24 x1 squared. We are not going to use the x minus 3 component. Okay, we are not going to use that component, and that is because if you look at it carefully from the diagram, you will see that between C and D, x minus 3 is beyond C and D. Okay, you see that it's beyond this one, so we are not going to use this one. I hope the concept is clear. All right, so we would go ahead and then so 30x squared minus 24 x squared x minus 1 squared minus 163.33 to be 0. You see this quadratic equation here, you will solve it, and then so 30x squared minus 24, so x squared minus 2x plus 1, that is if you open the quadratic, okay, should be equal to 0. I want you to take your time and solve everything here. Okay, if you solve this quadratic equation, so minus minus is plus, 24 times 2 is 28x minus 24 minus 163.33. Okay, no problem. Let's solve it together. All right, so 6x squared plus 28x and then so minus 24, and then minus 163.33. And what is that? So that is going to be minus 187.33 minus 187.33. That is 0. So please let's solve this quadratic equation quickly. I know you know how to use the calculator to solve a quadratic equation. So 28. Sorry, I think 24. So 24 times 2 is going to be 48. So this one is actually 48. So 48. Okay, so it's actually going to be 48. Okay. And then minus 187.33. So the final answer is going to be x is what? 2.87 meters. And then the next one is what? X is minus 10.87. But you know that the distance x cannot be negative. So we are not going to use this one. It means that the maximum deflection is going to occur at a distance somewhere very close to 3. And which makes sense because it will be somewhere at the middle, but it's not necessarily at 3. But it's going to be somewhere very close. Okay. So it means that the deflection is going to look like something like this. The maximum is going to occur somewhere here. And then it bends like that. So something of that sort. Okay. So the deflection, the maximum will occur somewhere here. And we are calling that distance from here to here 2.87 meters. Okay, so now we know the maximum deflection where it occurs. So now let's put it into the equation and calculate the maximum deflection. So to get the maximum deflection, you put the x that you got into the equation, which will give you the maximum deflection. So then what is the deflection equation again? So the deflection equation is here, right here. Let me copy it down here. All right. Okay, so this is the deflection equation. So right now that we have 2.87, we will put it inside. So at x equals 2.87, we are saying that y is y max. So let's put it inside. We've got EI y max should be what? 10 multiplied by 2.87 cubed minus 2.87 minus 1 cubed. But I see that this one, the 2.87, if you put it here, it will be negative. So it's going to be 0. We are not going to use the negative distance. So minus 163.33, 2.87. Okay. So what is going to be this one? Sorry. So we've got, let's clean this one. Okay, so 10 multiplied by 2.87 cubed, and then minus 8 multiplied by 2.87 minus 1, then cubed, then minus 163.33. What is that? 20.755. So the deflection Okay, so all right. So I think there was a mistake here. It's actually going to be minus 2. So if you multiply this, it's going to be minus 284.67. So minus 284.67. And then the value is actually in kilonewton meter cube. So then Y max is going to be minus 284.67. Then you multiply here by 10 to the power 12 divided by 2 times 10 to the power 5. And then let me check. So the EI 2 times 10 to the power 5, 85 times 10 to the power 6. All right. So Y max is actually going to be so minus 284.67 multiplied by 10 raised to the power 12 divided by 2 times 10 to the power 5, and then multiply by 85 multiplied by 10 to the power 6. Okay, so we've got minus 16.74. So that is the maximum deflection of this beam. So the problem has been solved. I want you to take your time and go through all of this step by step. Okay, so thank you very much for watching.